Hi, so today we're going to be talking about thermodynamics, which is looking at chemical transformations and determining whether or not they are going to produce more energy or take more energy, need an energy input to make them go in the forward direction. We're also going to be looking at chemical barriers, that some reactions take a lot more energy to go in the forward direction than others do. All right, so to introduce the topic of thermodynamics, we have to actually first talk about reaction coordinate diagrams. And these look like they have quite a bit going on, but in the reality, they're pretty simple to understand. So all molecules have energies associated with them. Some are more stable than others, and so you could predict there might be a couple of scenarios that occur in any reaction. You might have some reactants that are very stable, and they could undergo a reaction that would produce less stable products, so they would be higher in energy. So going from starting material to product, or reactants to product as in a reaction progress, you would actually be making higher energy molecules. The opposite of this would be that you have starting materials or reactants that are less stable for whatever reason, and they're going to be making very stable products. And so they go down in energy as the reaction goes from starting material to products. And one of the things that happens is that this energy that is, this difference in energy is either released or it has to be absorbed. So if your starting material is already lower in energy than your products, is more stable, and you're trying to make less stable products, so maybe the energy difference is something like this, that means you have to input that much energy to make the reaction go in the forward sense. We would call this an endothermic reaction. Okay. However, if your reactant's already starting at a higher energy level than your products, for instance, there's an energy level difference of about that much, and then you're actually going to get that much energy back out if you run this reaction. So we would say these things give off heat, or they are exothermic. And I think that we know a lot of examples of endo and exothermic reactions that we just intrinsically know about, right? So for instance, when you burn wood, it gives off heat, and because you're generating products that are actually more stable than the starting materials, and so that difference of energy is given off as heat, and you feel it. Some other examples might be, for instance, like these instant cold packs and instant hot packs. So these have chemical reactions in them, so you break them up and you mix up the chemicals, and they undergo the reaction. And in the cold pack example, it feels cold because what's actually happening is if you're holding it in your hand, it's actually sucking the heat out of your hand to power the reaction, to make it go in the forward sense. And that feels cold. That feels cold to you. Conversely, in the hot pack example, so you smush it up and it undergoes the reaction. Typically, actually, it's an iron to iron oxide, so it's oxidizing iron, and iron oxide, the rust is more stable than the elemental iron, and as a result, it generates a lot of heat, and that is given off and it's absorbed by your hand. Okay, so you might have noticed that I've only was talking about the energies of the starting position and the end position. And we're talking about the differences there. So this would be an example of an exothermic reaction. The one thing I haven't talked about is this barrier that exists here, right? So there seems to be a barrier. And the height of this barrier is actually going to determine how fast the reaction goes. And so just in the same way that one would think about maybe a sprinter doing a leap over a kind of a hurdle or something like that. If the hurdle is really low, then the sprinter has no problem, just runs right over. But as it gets higher and higher, this gets more and more difficult, and things begin to kind of slow down to the point where it actually stops. So if we were to get this super high, then the barrier would be so high that the reaction would not go. It would not go at room temperature, at least. And we call this the activation energy. And so we have these two properties of the reaction coordinate diagram. We have the thermodynamics of how much heat is either absorbed or given off in a reaction, and that's going to be the energy of the starting position and the end position, whether you're making more stable or less stable products. And then you also have this hill that you have to overcome, this activation energy that you have to overcome to make the reaction go in the forward sense. And some are really small and some are really big. Okay, so to illustrate this issue, you have these two different energetic constraints when it comes to different reactions. Let's talk about graphite to diamond. And so we've already talked about these are the allotropes of carbon. And so this is, of course, one where everything is trigonal planar, and so we have this totally planar structure of sheets, and these will slide back and forth over each other. And then we, of course, have diamond, which is all tetrahedral shaped. And they have very different physical forms. Well, in fact, graphite is less stable than diamond. And so when we're talking about, for instance, a reaction coordinate diagram, and over here we have the graphite, and down here we have diamond. So we would say that energetically, this is an exothermic reaction, that graphite would like to turn into diamond because diamond is more stable. And so the question might be, if you have a lump of coal, or a pencil lead, why doesn't the graphite just instantaneously turn into a diamond? And the answer is that this is an example of something that has an enormous activation energy. So the barrier is really quite large. And so this barrier is so huge, actually, that it takes immense temperatures and pressures to overcome this barrier. So the only times you typically will make diamonds from coal, or from graphite, is deep in the earth, where the pressures are great, the temperatures are high, and you have so much energy that it actually is able to overcome this barrier. We actually can synthetically create diamonds now from graphite. We take bits of coal, and we actually just in furnaces and under high pressures, we actually can convert them from graphite into diamond. We can overcome this barrier as well. So let me give you another example of a chemical transformation that has energetic barrier problem. And this is the idea of generating nitrogen for the soil, so nitrogen fixation. And so nitrogen fixation is a process that occurs relatively naturally. So we have a lot of nitrogen in the atmosphere. In fact, about 78% of the air you breathe is N2 gas. So there's a lot of nitrogen on this planet. But the problem with that is it's a relatively inert form of nitrogen. And as such, the nitrogen to be uptaken by plants, so the plants can grow, they can't normally use that form of nitrogen. And so what has to happen is a whole complicated series of processes, typically wherein this goes into the soil, and then bacteria in the soil will actually fix this. They'll actually chemically convert it into a more usable form, in this case ammonium, and sometimes it'll be actually oxidized further to the nitrites and the nitrates, and then this in the soil will be uptaken to the plant. And this is an important nutrient for the plant. And one of the problems is that as late as the 1860s, people were largely expecting that as the population of the Earth were to increase, that there would be widespread famine by about 1940. So they were predicting that people were doing models, and they were figuring out that the reality issue is that if you kept putting crop over crop over crop over a part of land, you would deplete the nitrogen. You wouldn't be able to grow more crops. And so as people, as the population of the Earth increased, that people would ultimately not have enough food to eat, because we would deplete the amount of nitrogen needed to grow food. And this was a very serious problem people were facing. Well, come around World War I, Germany had another problem, and that was that the German war machine needed nitrogen to make weapons. They needed to make bombs, actually, and so they needed to chemically synthesize some bombs, and a lot of explosive molecules have high nitrogen content. So trinitrotoluene, as an example, has 3 nitrogen atoms in it, and so to make it you need a nitrogen source, and they couldn't get it because at the time you had to mine these nitrogen-rich materials to kind of get and process the nitrogen. So they also set their scientists to try and figure out how they could potentially get the nitrogen from this really abundant source, which is the air. And this brought us to the Haber-Bosch process, and this is one of the most important chemical reactions that has been developed. So the Haber-Bosch process were developed by two German scientists, and as I said before, they were, although their process has been utilized to help generate fertilizers, it actually was originally utilized to generate ammunition and bombs. But the Haber-Bosch process figured out a catalytic process, and they actually used a platinum catalyst to help run this reaction. So they could combine nitrogen gas and 3 hydrogen atoms to make 2 ammonia atoms, NH3, which is a usable form of nitrogen. And so ultimately, they were able to develop this process, this catalyst, to overcome this enormous barrier, because once again, you're dealing with stable molecules, you're dealing with molecules that don't typically like to react, but they were able to overcome this process or these barriers with their catalyst and their process and generate ammonia from it. So obviously there wasn't widespread famines in the 1940s. We didn't run out of food, and we're not running out of food anytime soon. And this is largely credited to the Haber-Bosch process, which continues to generate fertilizer very, very efficiently and inexpensively from the nitrogen in our air. So we're able to fertilize crops even after they deplete the soil. And in fact, many historians now think about the fact that the Haber-Bosch process probably was one of the reasons why we have been able to expand our population so greatly, so much and so quickly, because we've been able to effectively feed people who would never been able to have been fed before from this chemical process.